Hello, y'all. Welcome to lesson 115 in my DP chemistry curriculum. Today we're doing reactivity 3.2.16. It is an HL topic. We're discussing electroplating, how it involves the electrolytic coating of an object with a metallic thin layer, and we will deduce equations for the electrode reactions during electroplating. We're just going to talk about them. It's going to be a pretty simple application of electrolysis that we learned earlier in this unit. So to start this out, let's just talk about what electroplating is. Electroplating. So, like I said, it's an application of electrolysis and is the process of coating or plating, where it gets the name from, coating or plating a conductive object with another metal, and this happens via electronic or electric deposition. Now, generally, we use the term deposition to talk about a gas being turning into a solid. That's the term for that phase change. However, we're now talking about an aqueous solution becoming a solid, which, when you think about it, an aqueous solution is nothing but a single ion surrounded by water molecules and essentially kind of behaving like a gas in that sense. So, this is what electroplating is, but how do we actually do it? Well, one of the easiest ways to look at this is just to look at an actual experiment. So if we have our container of some electrolyte, like we're going to do electrolysis, and we're going to connect maybe a piece of copper solid, and we're going to have some electrolyte, and that electrolyte is going to contain copper ions. We'll discuss, and it'll be pretty obvious as to why we don't want a different type of ion. We'll connect that with a power supply. We're going to make sure that copper is our anode in this case. Now on our cathode side, we can plate anything. So for instance, a metal spoon. Let's say this thing is solid iron. Now this is, of course, our cathode. And completing our diagram with our flow of electrons, we have electrons moving through our uh, electrolysis setup. So they're going from our anode into our cathode. A couple key components here is number one, we need a power supply. This is still electrolysis, so this is non-spontaneous. So we need to include our own power. Furthermore, we need a conductive cathode. This is going to be the object we plate. And so it can be metal, which is always going to be conductive, but it could also be something like platinum, and that would work just as well, or graphite, which is non-metal but still conductive. Then we need our metal anode. That's going to be the metal two plate. And then lastly, we need our electrolyte. So it needs to be a conductive solution. Again, this is still electrolysis. And lastly, it needs to have the metal ion of anode. All right. So like any general electrolysis, we're going to develop a charge here, a negative charge on the cathode. And our Cu2 plus ions in solution are going to come here, grab those electrons, and start depositing on the surface as solid copper. And that forms our thin plating. Now, as we remove copper from solution, we actually need to add back copper from our anode. So this is why it needs to be the same thing. If we actually have two different metals, then based on their reduction potentials, we'll have possibly different reactions and different alloying going on. It's much harder to control, and we have to then start looking at a bunch of various factors as equilibriums will shift as well. So we use the same electrolyte ion as our metal anode. So just to recap that, like any electrolysis, electrons flow into the cathode, oops, cathode, as it's being reduced, red cat, and metal ions move to cathode. They're pulled by those electrostatic interactions where they bond into thin layers. This is literally what we call plating. So this is plating. Now, we actually have a different term. You can still use plating, but if you're taking a metal and putting it on a metal, so when we have a metal cathode, we can refer to this as being alloyed. Remember, alloyed is a term we use when we bond metals together. Now, the important thing is, or one other important thing is we noted that copper is coming off our anode, which actually means that as this reaction progresses, so as that reaction progresses, our anode is eroded. Anode is eroded. Those are all moving, all those metal atoms are becoming ions and migrating to plate the surface uh, of our cathode. So we need to replenish that if we want to continue it. Um, and this is happening because the uh, anode is oxidized to replenish metal ions in solution. So this is actually a pretty simple reaction. There's a lot of people and scientists online that do this over YouTube and stuff, and you can set up a pretty easy electrolysis setup, even in your own backyard, provided you have the chemicals. And it's very simple to plate one metal onto another. Now, one thing just to watch out for is that, remember, we use metal electrodes for this, especially at our cathode, or sorry, especially at our anode. But what happens if we use an inert electrode at anode? Well, now this won't replenish, it won't react. This will actually cause a preferential oxidization of water, uh, producing O2. Now, that would be instead of the anode. And so you may have oxygen gas bubbling. If that's happening, you're seeing the preferential oxidation. Now, that also means that if you're pulling water or you're pulling oxygen out of the solution, you are essentially doing the electrolysis of water that we covered in the previous unit. So we definitely want to have our electrode to be the uh, our electrode at the anode to be the metal that we are trying to plate onto our surface. Anyways, this is about everything there is for electroplating. I hope this helps and have a good day.